Hello, I'm Robert, and this is to help you if you're scared about this idea of the forced vacuum decay, the idea that something could happen to the entire universe. And so this is my space cows argument, which Tommy Markkanen has he endorsed it. It's a good way of explaining things. And so to understand, the proper way to understand this is in terms of the past light cone. And this means, if this is Earth, then we need to look at all the places. If we look out and we look at the galaxy in a very far distance, and as we look further and further away in space, we look further and further back in time. And so, because the light is coming to us directly from galaxies, this one, for instance, is 6 or 7 billion light years away, which means it's 6 or 7 billion years younger than our galaxy. It's only 6 or 7 billion years old, because it's about halfway back. So, in all the trillion galaxies we can see in all directions, vast distance, then the past light cone consists of all those galaxies, and then inside it is all the past of those galaxies. So this galaxy has been around for 6 or 7 billion years, as we at the point that we see it, in very far away. And if there was a forced vacuum decay in any of those 6 or 7 billion years in its past, then because it propagates the speed of light, it's already happened here. So we know it hasn't happened. So if you look at this idea of a mythical space cow, and so long as there's nothing especially tasty about the universe at this point, you just have this idea of fanciful universe-gobbling space cows, and they just will randomly gobble the universe at some point. And then it's not a real thing, it's just made up, and it's meant to be funny and not scary. So if there was a space-gobbling space cow that nibbled at the universe at any point in this 6 or 7 billion years history of that, or our 13 or 14 billion years history, then we wouldn't be here. So we know that we soon know that no space cow ever ate our universe in any of those 13 to 14 million years. 13 to 14 billion years, or 13 to 14 billion centuries. So this is how we know, even without any of the actual working out the mass of the Higgs field, this is how we know that our universe is very safe indeed, because it just lasted for so long and nothing has happened. There's nothing special about our millennium. So this comes to our space cow's argument. And if I just go down and remind you of it, if you haven't seen it before, and this is the idea of the mythological space cow, and this is a maths joke, a physics joke, and the idea of a space cow, of a cow, a spherical cow in space. But there's nothing special about our current millennium, because millions of stars and planets are born from gas clouds every day, and other stars getting old, millions of planets orbiting stars, millions of galaxies continue turning, and it's much the same as it's been for billions of years. So if I was trying to help someone scared of mythological space cows, I could say, no space cow has eaten our universe for 13 million millennia. And there's nothing special about the millennium just now. It doesn't get especially tasty for mythological space cows at 13 million millennia. So even if your idea was theoretically possible, there's no realistic possibility of it, because in this way we're safe from anything that can happen to the entire universe. And so of course we're safe from forced vacuum decay, because we're safe from anything, as long as there's nothing especially tasty about our universe. So what I've found is that some people don't have a strong background in maths and don't really appreciate what a billion or million really means. So then that's why I made this pile of ends. So if I go and bring it up now, and hopefully this is in the right place, there we are, then this is a very long file. You can see the scroll bar here. And if I just do a page down, scroll bar doesn't actually even move. You've got to do lots and lots of scrolling down before you actually even see the scroll bar moving. Now you can see it just gradually, very slowly moving. I'm scrolling at a furious rate. And I'm just pressing the key down and I'm letting it repeat. There are 138,000 rows, and each row has 100 M's in it. Each M represents a millennium. So what this represents is that this is the Big Bang, and then this is the first 100,000 years from the Big Bang, the second 100,000 years, the third 100,000 years, and so on. And then we've got 138,000 of these 100,000 year periods. So if you keep on going right down to the end, then Jesus was born there, just at the start of that M. The Vikings, they happened in this last M. The Egyptians were a little bit further back. The Sumerians a little bit further back. Humans first evolved around here. The first cave paintings would be somewhere around here somewhere. The very earliest one somewhere along here. Then before that we had the early ancestors of humans, and then going back and back and back, you'd have to go back quite a few pages to get to the dinosaurs, and further back and back and back, and you get to the first microscopic creatures in the sea that were more than one cell. Then you get to single cell life, and back and back and back, and then you get to when the moon formed and the Earth and Moon formed, then when the Sun was born, and that's only about halfway back to the Big Bang, even then. So in all that time, nothing has happened. No mythological cow has tried to eat our universe. So you just mean one M. Just imagine these M's coming one at a time, and M. Imagine you're watching, you're seeing one M after another, and this one M, another M, then other M. So there's it would be just not ridiculously unlikely for anything to happen in the next M. Just not a realistic thing, just not something to worry about. And then if you went to use the actual mass that we have for the Higgs field, and it's not just this, the number of M's we can expect to wait. So we can expect to wait, a significant fraction of the M's that we've already had, and that is a realistic. That is that's called Bayesian inference. You can just infer that. That's a reasonable and scientifically valid way of reasoning about this sort of thing. And then if you look at the actual mass, then it's actually, you expect it to be stable. That would be the most likely of all. That's what everything else is. And you would expect, if there was any possibility of, so all of this is pretty much the same, except the very first microsecond, and just the first fraction of a microsecond of that very first M. Back then, for a very brief time, the universe was incredibly hot. And so in that very first microsecond of that very first M, then the scientists, our current science says that if the force vacuum is not completely stable, if it's metastable, then it's metastable means it's a little bit like say a table, or like something. If you imagine a bowl with an apple in it, then that's metastable, sitting on a table. Then the apple isn't going to jump out of the bowl, but the apple would be in a much lower energy state if it was on the floor than if it was in the bowl on your table. So the apple is in a metastable state, because if it was completely stable it would be on the floor, because the floor is lower energy. So that's what metastable means. And so the universe is metastable in the sense that it's inside a kind of a ball thing, and it would have to jump out of the ball to go into a lower energy state. But now, right at the very beginning, everything was jiggling very, very, very fast. And imagine that now the apple's bouncing around, and it bounces 2 meters with every jump. Then it'd be extremely unlikely that it stays within the ball. You're just precisely jumping up and then falling down to the ball again, and up again. It's jumping in random ways. It'd be incredibly unlikely for your apple to stay in the ball in the very first microsecond, but it was just so very hot. And when things were bouncing around, and it turns out that the Higgs field would be kind of wiggling around too, and so it just wouldn't, you wouldn't expect it to stay in the same state. So that is why many cosmologists think that actually this whole idea about an unstable Higgs field, metastable, not unstable, it's not unstable, metastable, like an apple in a bowl, they think it's really like an apple on the floor. But even if it jiggles around, if you've got an apple on the floor, and if it bounces up and down meters at a time, it's got nowhere else to go, it's already at the lowest point. So they think that the early universe was most likely like that. Or else, it could be on a ball, but it's gone down to the floor and it's now on the floor. And it's got nowhere further to go. So it might be metastable for a little while, but it would have gone to totally stable in that first microsecond. So that's what many think, and they think, well, why does the Higgs field look as if it's metastable? And well, we often have things that we have kind of gaps in our thinking. So we understand the universe very, very well to many decimal places, but there are always a few things that we don't quite understand, niggling things, and then they lead to new developments sometimes, like quantum mechanics or like general relativity. And we actually have niggling things that we don't understand. Quantum mechanics does not explain general relativity, doesn't explain gravity. We can't use quantum fields, and we can't use the methods of quantum mechanics, the particles and the quantum mechanical equations, to explain gravity. Then, if you look the other way around, if you look at general relativity, it's all about curved space. There's nothing there to explain why the space is curved. There's nothing there to explain matter and what it's made of. So the two theories, they're not talking to each other, and they can't explain each other. So it's clear that we are missing something here. We can just we can kind of wrap the quantum mechanical idea into the gravitational idea, but the whole point is, you see, that the general relativity curvature is curved by the mass in the quantum mechanical picture. But there's no mechanism for the quantum mechanics to affect the curvature of space. So why would it be curved in that particular way? And how can we understand that if you move a heavy thing around in the quantum mechanical description, that it changes the curvature of space in the general relativity explanation? And we've got just no explanation of this at present. We just fudge it and say, if you move mass around, then the general relativity will move with it. If Mercury orbits the Sun, then we just set up a gravitational curvature of space that follows Mercury around the Sun, but no explanation of why it does that, and why it doesn't just stay in one place while Mercury keeps going. So we are clearly missing something, and something pretty major. So there's lots of other things that we're missing as well, and so doesn't mean that it's going to suddenly change our physics and our understanding of physics, because just like when we discovered general relativity, this space-time was always curved, if it is curved, and if that's the best way of understanding it. but the Newton gravity with a flat space-time was a pretty good approximation. So we didn't have to throw out all the results of Newton. Indeed, most people, most physicists, most of the time will be using Newton mechanics because it's far simpler equations. And if you want to calculate, how the movements of a plane or a ball or a rocket or something, then you use Newton gravity. You won't need to use general relativity, which is fiercely difficult to calculate with. It'd be very, very difficult, for instance, to devise a way to launch a satellite using general relativity for all your equations. I mean, imagine if SpaceX had to use general relativity, they'd be still at it trying to work out how to launch their satellites. They just wouldn't know what to do. It would be really very difficult, all their calculations. So we expect our theory to we expect there to be new things to discover. And so do I talk about that here? I think I do, just up here. Right, yes, in standard theory, our best guess is that it won't happen for not just millennia or millions of years, but so many M's. So this is based on the standard theory, so I just gave the space chaos thing. But now, I haven't mentioned this bit. So if I just go up there to, go back to this one, then if we were to use the standard theory and how long we have to actually wait in the future, then instead of being just a substantial fraction of the M's we've had so far, it's so many M's that even if you had an M for every single fundamental particle, not just atoms, every proton, every neutron, every electron, in the entire visible universe, in all those trillion galaxies, and all the stars and all the planets, if every single thing was an M, you wouldn't have enough to express the number of millennia that we expect to have to wait before the false vacuum decay would happen. So it's just so close to stable. And it's very bizarre to understand how can it be so close to stable and not actually be stable. And why would it be so finely balanced? Probably because it isn't. Because we're missing something we're not understanding, and this is just some kind of glitch in the way we are reasoning about the universe because of us not being, maybe because we're not able to combine general relativity with quantum mechanics. And then when we do that, perhaps with string theory, but we haven't got any evidence to support string theory yet because we just can't do the experiments. But maybe someday we prove it's string theory. But if we prove it's string theory, then we won't have a false vacuum decay anymore. So that's one possible solution. And then another idea is that we can't explain. Yes, here we are. This is the section. We can't explain dark matter. So dark matter it's not matter that obscures things. It's not like a dark cloud. Dark matter is matter you can see through. You can put your hand straight through even dark matter, and it will just go straight through it, and it won't notice through your hands. You can't see it, you can't touch it, and it can't touch itself. It'll just dark matter passes through other dark matter, without even noticing it. The only way it interacts is using gravity. So it's very, very hard to detect. What kind of instrument are you going to use to detect something that's only got gravity? Because with the gravitational field, gravity is a very weak force. If you've just got a few particles going through, and the only way they interact with our matter is gravity, how are you going to ever see them? So they're very, very hard to spot. And there are some ideas, mainly they look for them by ideas of matter that is almost dark. So there's tiny, tiny interactions that it can have. And if you've got vast numbers of them, countless trillions of them passing by, then very occasionally, maybe once every decade or something, one of them might interact. If you have a very, very big So they have these experiments where they look at thousands of tons of water in a mine deep below the surface to make sure the only thing that can get there is dark matter, because it's and very, very rare that anything else gets there, because it's blocked out by anything else that could confuse you. And you choose some kind of material like water, for instance, and then you choose a material that the things we know about can't interact with it and aren't going to do anything, aren't going to confuse the experiment. And then you just watch and you see if there's a little spark of light. And if you do spot a spark of light, then you say, maybe that's dark matter. And there'll be some things that it can do, like for instance neutrinos. So a neutrino is a thing we know about. It is a kind of dark matter that we know about, but it's not enough to explain the reason we have dark matter is we're trying to explain why galaxies are held together and why the universe is held together. It seems to be more gravity than there should be, from what we can see. So, and it seems to be like, for instance, galaxies are kind of flat disks, but there's something that suggests there's a spherical distribution of mass in the galaxy. It doesn't seem to be flat. If you look at the way things move under gravity, then they don't move like they would if the galaxy really was a disk. So that's why it has to be something that can't interact with itself, otherwise it would have flattened into the disk. Or it can't interact with with ordinary matter. It can't interact with itself and make another galaxy that's at an angle to ours. We'd notice that too. A kind of dark matter galaxy, but its gravity would be very different from what we spot with dark matter. So that's why I think this stuff exists. From the way stars move in galaxies, and they move as if there's an awful lot more mass there than we can see, and this extra mass was in a spherical distribution. So, and then if this dark matter, it maybe goes through, these particles could be going through us every day. We've got trillions and trillions of neutrinos going through us every day, but there are not enough of them. So there must be even more of some other thing that's even more invisible than a neutrino and even harder to spot. So if we do someday manage to spot this elusive dark matter, well, it might well turn out that it interacts with the Higgs field, I should say. And if it does, it could be the Higgs field gives it mass. Then if it does, then that would mean apparently that the universe is and always was stable. I don't understand the mass of this, I'm just reporting what they say. And then another way it could happen is if there's a second heavier Higgs particle that we haven't found yet. That's another way it could be that it could just mean, it's always been stable. And then you would look at your theory and then say, why, if without knowing all this, why did it seem so close to seem to be exactly on the borderline, and we may find some interesting kind of way that the theory works to explain why it is that without the extra Higgs it looks as if it's completely on the borderline. It may be just a coincidence, it may be there's some deeper reason for it looking like that. So that's many cosmologists think that this may be what's going to happen eventually. But because it's so very, very difficult to look for dark matter, and some of the other things like a second Higgs, it might be that it requires energies too high for us to look at it yet. And then combining general relativity and quantum mechanics, then nobody's quite sure even what experiments to do to test to find out which is the right way to combine. For instance, string theory, nobody really knows how to test to see if that is correct. So these are all things that we may be able to sort out someday. We might be able to do it in the next few decades. We mightn't be able to do it for centuries. It might take millennia. It might even be that this is something that people are still puzzling over 1,000,000 years from now, and it's just extremely difficult to answer. So you shouldn't be trying to get your hope up and just wait and hope that someday we're going to find the answer here. But it might well be that the universe is just fully stable and not even metastable. It's not like the apple in a bowl on a table. It's like an apple on the floor. It's got no energy to go to. So that's well possible. And then going back to this idea of our best understanding with standard theory, then this is a photograph of the true North Pole. Does that work? Yeah, that seems to work, because I'm just checking on my extra monitor. It's the right size. So this is the geographic South Pole. There's a ceremonial South Pole, which kind of got all the flags of all the nations around it. But this is the actual geographic South Pole. They have to keep moving it, not because the South Pole is moving, but because this is a moving ice sheet. An ice sheet very, very slowly moves, even at the South Pole. And so they have to keep moving this pole, this metal spike for the geographic South Pole to the right place. That's why there's only the US flag, because I think that they're there, and they're just the ones who have to keep moving it. And otherwise they'd have to be moving all the flags every year, and that would be just a very long job. So they just move this little pole. Then they have a ceremonial pole for dignitaries and so on to go and have ceremonies, or celebrate something or whatever, which is just a little bit away out of the picture here. So anyway, that's the geographic South Pole. So is it possible that so I just count 1,000, 2,000. During that time, I counted 1,000, 2,000. Do you think it's possible that 14 Chelyabinsk-sized asteroids hit within 1 meter of this pole? Would you think that, well, we should go and check the news and see if that happened? And I'm not talking about ones that are all in one big asteroid, but in completely independent orbits. Then surely you'll just answer no. It's just not possible that 14 asteroids in completely different orbits, and they hit on average the entire Earth on average once a century. So whatever size is the right size to hit Earth once per century, and the Chelyabinsk one is probably about the right size. Then could they all have hit that pole in that second? And I'm not going to go checking the news to see if it's true, because it's obviously impossible. So this is the sense in which it's impossible that the false vacuum decay happens in the next several billion years. And not just for us, but over that entire past light cone. So if I go back up there, in that entire past light cone, if you take that galaxy and go forward 1,000 years, and even you're going forward several billion years into the future, even going forward several billion years, that's like that 14 asteroids hitting in 1 second. That's how incredibly unlikely. Indeed, it's not really what you'd normally call a chance. It's what most people would just say is flat out impossible, because that's how most people think. They don't have these. Mathematicians have rather strange ways of thinking about these things. So if I were talking to mathematicians, I'd say it's got a probability of ... But we don't use the mathematical word probability. Is not used in the same way as ordinary people use it, because we'd call this an impossibility in ordinary language. So and the math is quite simple, and I work it out in the link page. So it's not even remotely realistic, and this shouldn't give anyone even 1 second of anxiety. So hopefully at this point this has helped you to get over some of your fears of a false vacuum decay, and just remind yourself, and just go back. There's those two things. There's the 14 Chelyabinsk asteroids, that works for most people, and then there's all those M's, which I can just bring back to, and just remind you. I'll just quickly remind you of the M's. So just remember, Big Bang there, started there, and then these vast numbers of M's. You could go. I'll put a link in the video description. You can scroll down it and try scrolling down 1 page at a time. Remember, Jesus was born there. Human beings first evolved there, and in all that vast time, it's not happened. So even if it's a mythological space cow zone, no matter what weird thing that you might read about, some bizarre new idea for a way that the false vacuum decay could happen, just remember all those M's. And there's nothing special about our millennium, and so we're safe. Just not realistic at all. And I been debunking this and helping scared people for some years now, and never for even one fraction of a second have I had any concern about the universe, because I understand the maths, and I know this just can't happen. It's not realistic.